Hello and good morning, everyone. Just wanted to welcome you all. Thank you so much for joining us today. We will begin this webinar momentarily. Hi, Dr. Prasanna.
Hi.
Hello. Okay. So people are still coming in, but in the meantime, I just wanted to go through some introductions. So hello and good morning again, everyone. My name is Tiffany Tay, and I am the Executive Director for Annual Giving and Alumni Relations at the USC Viterbi School of Engineering. Welcome to our Viterbi Live webinar featuring Dr. Viktor Prasanna. So we have started this Viterbi Live series to bring stimulating and timely content to you during this challenging time. Some of you may have tuned in already to some of our webinars, so you may already remember Dr. Prasanna as a featured speaker at our Digital Technologies for COVID-19 series. In addition to participating in all of these live sessions, Dr. Prasanna is the Charles Lee Powell Chair in Engineering and is a professor of electrical engineering and the professor of computer science here at USC. He also serves as the director of Center for Energy Informatics. His research includes high-performance computing, parallel and distributed systems, reconfigurable computing, cloud computing, and smart energy systems. Before Dr. Prasanna takes a screen, please know that you can enter in your questions at any time in the Q&A box, located at the bottom of your screen. We will try to get to as many questions as we can at the end of the presentation. If you want to ask your question verbally, please click on the raise hand icon next to your name at the bottom, and we'll try to get to that as well. Without further ado, please join me in welcoming Dr. Viktor Prasanna.
Thanks, Tiffany. Let me share the screen. Thank you everyone for joining us today. So I'm going to be talking about some recent work we have been doing in looking at the COVID-19 spread and then understanding this from using some machine learning techniques. So I'm joined here today with my research associate Ajitesh Srivatsava, who is also joined here as a panelist. He will also answer some questions towards the end, also look at the visualization tool that we have developed as part of this. A lot of the work we are doing in this, in my work, what I present today is part of the data science lab we have at USC. You may wish to visit that website, dslab.usc.edu. So just a general notes about this presentation. I have prepared this presentation to be accessible to a broader audience. So in this context here, you will see some introductory material also is included as part of this. So some of these details may be skipped if you are somebody who is already working in this space. If you're looking for more details of the technical details of this work, I encourage you to look at the archive website where we have a particular publication that we have posted there that goes into the details of the modeling, the training that we performed on the machine learning models that we developed, as well as some of the more details of the experimental results we have obtained in this context. Also that towards the end of this talk, I will give you some details of a visualization tool, a user interface that we have developed. And this particular tool should be carefully used. It is not meant for general public consumption in which you may not know how these models are trained. So be careful if you do decide to use the tool and go through the details of that before you actually make use of the tool to make some predictions in your neighborhood, for example. So I've organized this talk just to initially give you some overview of the work we do in my lab. Following that, I'll go through some details of machine learning just to make this talk self-contained. Then I will talk about some of the earlier work we have been doing in the data science lab. In particular, we have been looking at this problem. Ajitesh has looked at this problem before. I will go through some details of that. Before we go into the actual work, the main topic of this discussion today is to look at how machine learning models are developed by us and how do we train these models. How do we use these models to understand based on the available data, what kind of predictions, forecasting we can make in that context. I will also have some comments to make about what is the role of machine learning in these models. And finally, I'll go through the visualization tool and some of the ongoing work we have and conclude this presentation. So I expect to spend about 25 to 30 minutes overall, and the remaining time that we will use for discussions and any questions you might have at the end of this presentation. Moving along, as the data science lab is a lab that I established several years ago at USC. We look at number of applications of machine learning optimizations in this context. I've shown some examples here. We are looking at problems in smart oil fields, smart grid, system design. For example, if you would like to design a computer architecture, we ask some questions such as how do you optimize the overall system performance given various constraints you have in designing such a system. So we look at such problems in the context of system design applications of machine learning in that context. We also look at problems in internet design, looking at how to, for example, forecast the traffic in the internet backbone by using machine learning techniques. In the context of smart oil fields, we look at machine learning techniques, data science techniques, to be able to, for example, understand what is the benefit of doing a particular kind of makeover on a well, and then how much does it impact the production of oil if you were to do a particular way that you're going to be pumping steam into the oil field to be able to extract more oil out of the oil field. In the context of power grids, we would like to understand, for example, given the historical data, how can you predict at that point what is going to be the load on the system at a particular point or a particular interval of time. So these are the kind of example problems that we study in my lab. And I've shown here the data science lab URL here. You might want to visit that site there to get more details of the various projects we are working in that context. So let me now quickly go into some details of machine learning context before I get into some details of the work we have completed before, and also the application of these ideas, the machine learning ideas in the context of the epidemic prediction. So let's just quickly go through what machine learning means in layman terms. Again, this is just a simple introduction here so that we are all on the same page as I go into the details of machine learning techniques that we have developed as part of this. What you see here is typically we are used to looking at a computer as taking some input program that you wrote, taking some input and producing an output. That's a typical scenario that we have for a computer program. In the context of machine learning, you are given data and maybe some kind of a labels on the data. That is the output I'm talking about here. And the machine learning program produces as output a program as the output, as a model of the input representation you have. That means we can use this program to be able to understand better, infer something about a new data that may come into the system. So the distinction you need to make here is that in the previous case, we had a program we wrote and it produced an output. In this case, we have some system here, a computer program, which is kind of learning, which is kind of adapting. That's one of the two possible definitions I've shown here on the left-hand side. So in this context, we obtain a model of the system, the model of the data that is given to us. That is what is the output of this machine learned program that I'm showing here as the output of the machine learning task. So in this context that we are generating a piece of code or a model, and that model is a representation of what is inherently that is there in the data that we learned, that we modeled by using this particular machine learning technique. I'm just giving some examples of machine learning applications here. There are a number of applications over the years. It's a very, very important area of research, as many of you might know. For example, you can do object recognition, recognize and tag objects. I've shown here examples where you want to identify here, there is a bicycle, there is a dog. Or you might also want to use these techniques for document classification. For a given input document, you want to classify it. Perhaps you might say in your case of the mailbox, you might have, it belongs to a legitimate input you have, an inbox, or it could be forwarded or routed to the spam folder you have on your computer system. This is an example of a classification that you can do by using machine learning models. There are a number of other applications. It's anomaly detection, fraud detection, for example, or playing games. These are all the number of places where number of tasks where machine learning techniques have been widely used over the years, with some very, very good success in all of those domains we have. Just examples of various machine learning algorithms that we will be talking about today for as part of our implementations. For example, we can talk about classification. Given the input data here, we would like to assign a category to each input data. For example, you can say, given the input document, say it is going to be in part of the inbox, or is it going to be going into to one of those spam folders you have. Or you might do clustering. That means given the input data, you want to partition that input data you have into homogeneous groups. That's the classical clustering technique that is studied in machine learning. Or you might also do regression analysis here, predict a real value for each input item. That means we're doing prediction here based on historical data, what we have learned, the models. This is one of the important things that we will do as part of this talk here, to be able to predict how a particular epidemic is spreading through a neighborhood or through the system. Also, I've given some examples of learning here, just to kind of give an overview of what happens here. For example, a lot of what we do today is going to be supervised learning here. That means the learner, the computer program that we talked about earlier here, receives a set of labeled data. That means that whatever input you have, so you have some kind of a ground truth at that point here. And that information is used for us to be able to learn the model, learn the input data, and then extract some information out of the data here for us to be able to create a model out of that. So data is going to be in the form of input, whatever is the data point you have here, and what is the correct output corresponding to that input data. And that information, a batch of them is provided, and the computer system, the machine learning program here learns this particular model by using this label data. This particular technique is called supervised learning, which is the technique that we are going to be using as part of our prediction models that we develop. There are also other techniques which I will not go into details. Unsupervised learning, for example, in this context, the data is given to us as inputs. For example, clustering is a classic example of unsupervised learning. Or we can also do reinforcement learning, in which we constantly learn in the environment. That means we react to the environment, we learn what kind of activities are taking place. You can define some function that maximizes the return that the model that you're trying to learn here. So there are a number of these techniques that are developed. For example, some of the techniques that are used for playing tic-tac-toe, for example, is the reinforcement learning, where you constantly interact with the environment based on the outcomes you learn, and then update your models as you go along. So just to make this talk self-contained, I've given some terminology here. We are going to be using some of this terminology as we go along to be able to talk about what is training. We talk about training data here, and then use the training to understand by using the various parameters. I talk about hyperparameters here, which are parameters that are used in the training process. The inference here refers to, given that you have a trained model, and then use the model, and given input data you have, you want to understand at that point what this inference, what is the value associated with the output for that particular input, that is the inferencing we have. And we can also talk about, in this context, how good is your machine learning algorithm. We can talk about accuracy. Very simply, we can talk about in terms of what is the number of correct predictions you have over all the predictions you made. That's, for example, if you're doing classification tasks, we can talk about accuracy in that context. Also, later on in this talk, we will talk about what is the accuracy of our predictions. We use a classic metrics that are used here, what is called MAPE and RMSE metrics that is used. MAPE refers to the mean absolute percentage error, which is the average percentage difference of the predicted value from the correct value. That is a very simple definition. And the root mean square error is also one more technique that is used here, which is somewhat technical term here. So, but we will use these two here, MAPE and RMSE, as metrics here for us. When we have this time series data, we predict from that, and then we would like to be able to understand what is the quality of those predictions by using these two metrics as we go along. Let us go along. So I think the basic, the premise of this talk here is that we can predict the spread of the epidemics, and then we can predict it accurately by using those performance metrics I talked about here. Prediction here means that we are making some statement about the future event. For given some historical data here, we learn the model, and using that learned model, we go and predict what is going to be in the future over a particular window or a short term or a long term. Again, we can talk about short term predictions. What is short term, long term depends on the particular kind of a prediction you're trying to do. In our context, we might want to predict over the next 1 week what is the possible potential spread that may be there. Or in the long term for us, maybe that in a matter of few weeks, what happens? Let us say in the next 1 month, what is going to be, that's going to be considered long term in our context here. Also keep in mind that as you predict over a longer horizon, your uncertainty increases, meaning that your accuracy will drop. So we need to keep that in mind as we do these predictions here, so that understand that what is the quality or the accuracy of the prediction you might have by looking at the time window that you have over which you predict those events. Now, let me just go quickly some examples of the work we have done before I get into our techniques that we have developed for in the context of COVID-19. This is an example problem I'm talking about here in the context of smart power grid. A classic problem here is that you have these inputs and you want to be able to predict based on the data you're getting from, for example, the metering infrastructure. You want to understand here, can you tell me over the next 1 hour, what is going to be the load on the system? If you understand what the load is going to be, you can do some various controls in the system, real-time controls in the system, so that you can make sure that your transmission, how much you're consuming, how much you're producing is going to be exactly matched at every instant, so that the smart grid system is going to be stable to operate at that point. So one particular technique that we developed here as part of a large project from the US government is looking at partitioning this data into the various time intervals you have, understanding for each one of those intervals, what are the particular models to be used, and combining those models to get the final output prediction we have here. This particular technique is what is called ensemble learning here. That means that you learn various models and combine the models. Even the weights that is shown here, the prediction weights I'm showing here, these 3 weights I'm showing here, these are the weights that you learn we can learn these weights here and then create a complete ensemble model based on that. So what I'm showing here, just a quick result here, showing that for those 2 error metrics that I talked about earlier, by using the ensemble model, you can significantly reduce the error by using our techniques, by using our machine learned model compared to classic techniques in the literature for solving these problems, for example, by using ARIMA models or by using a single model in that context. Moving along, this is a nice piece of work we did in my data science lab for looking at the smart oil field. The problem here is that in the oil field operations, there are a very large number of wells. For example, if you go to Central California, and some of these wells are used to inject steam, and then we want to find out what wells to choose at a particular point so that we inject steam into them, and then by doing that, we recover more oil out of that. And we also solve this problem by using a deep learning model. I'm just showing some examples here. We learn the intrinsic features of the model and use those features to be able to go through a predictor here to understand which wells to be injected steam into, what is the potential impact of that. And then we were able to get some significantly improved performance compared to state-of-the-art techniques here by using these kinds of machine learning to understand the intrinsic features and thus use those features as part of the prediction. Just one more example, one of my doctoral students is working on this problem. In this particular case, that we want to understand what is the internet backbone traffic. As you all know that in the current last several weeks, based on the work from home situation, the traffic on various backbone, various kinds of applications has dramatically changed. That's the example I've shown here on the right-hand side. So we want to be able to predict this traffic here so that we could be able to better utilize the resources we have, give a better experience to the end user. So we developed what are called LSTM models here, long short-term memory models. Using those models, developing ensemble models based on that, we are able to very accurately predict what kind of traffic will be there over the next time interval and use that information to be able to improve for example, the quality of service, quality of experience for end users in that context. Finally, before I get into the specifics of the COVID prediction we are doing, I would like to present here some of the earlier work we did here in this context. The left-hand side diagram is something that we are going to talk about. This is a particular model that we developed earlier. This was done as part of my research associate, Ajitesh, who's also participating here in this call. Ajitesh is received a special award as part of his PhD thesis work he did with me several years ago. This was a DARPA challenge in which he participated. At that point, in the time frame of 2014-15, you might be aware of the chikungunya propagation in the Americas, and there was a lot of interest in understanding what is the impact, for example, of travel as this virus spreads around the North American continent. And he received a very special award from the DARPA director, that is R.T. Prabhakar, who was the director of DARPA at that time, who is to his left in this diagram. Ajitesh also did a lot of interesting work as part of his PhD thesis, which looked at various network propagation models, use of machine learning in that context. Some of those ideas are being used here in this presentation as part of the COVID prediction that I will talk about next. So next, I would like to go into details of the particular model that we developed and also the particular training that we performed in that context. What are some of the initial results we got by using those models, and also highlight the role of machine learning in that context. So I'm going to a little bit speed up here. So why do we need to forecast here? So again, by doing forecasting, we can do, for example, better resource management in that context here. Or for example, if you want to come out of the stay-at-home order, can we understand what may be the impact of those orders based on some historical data we have collected about various locations we have around the state, around the country. And also that we can also use detailed models. If you have accurate models, we can also use those models to be able to kind of simulate the various scenarios, understand what is the impact of various orders at a particular point, and then how it may impact if we release those orders at that point. There are a number of modeling choices. What I'm showing here in the green is the particular modeling choices that we have taken. We are using generative models. We'll talk about details of that. And also as we go along that, we also took that particular model and then showed that by kind of adding more parameters here, by getting a more detailed model. I talk about this model in detail, and then we do certain amount of linearization here to be able to train this model here, and then we choose the various hyperparameters in the training process so that we get accurate results by using comparing against historical time series data you have. Just quickly, I want to kind of say that these kinds of models exist. One of the classic models is the SAR model here. That means we understand that individuals, for example, can go through 3 states here, 3 compartments it's called, in which you go through the susceptible state or infected state here, or go to a recovered state here. These are the various parameters, rates at which you go here. You can write those equations. Again, these are all well-known models in the literature, what are called SIR models and SI models. What we did in our research is to go into details and then define a new model here, which is a more detailed fine-grained model. We call this the heterogeneous infection rate with human mobility. So what you see here on the right-hand side is one of the models that Ajitesh developed earlier as part of the DARPA challenge. And we also tried to model here explicitly the impact of travel. That is what is this various regions you have here, C1, C2, C3. And then, so in this case here, this factor delta here is capturing the impact of the mobility in the system. And we also have this table here, the variable f defined here, which captures here what is the amount of mobility from various regions into this particular region C1 we have. So just to go into some details of this model here. So there are 2 parameters in this model. In this specific model, what we call the heterogeneous infection rate with human mobility model. We explicitly model here the various states we could be in. For example, a person could be infected, a person could be in various states. That's what the states I1, I2, Ik depicted here. And this constants you see here, betas here, beta 1, beta 2 here, these are all the rate at which you can propagate. For example, beta 1 refers to if you are infected at time t minus 1. And what will be the infection rate at that point? That's what is the constant. This beta 1 is defined here. And then the travel spread here is captured by using this quantity here, which says what is the amount of mobility that is coming from a region Q to region P here. And also, we also have another constant here, delta, which captures the impact of that mobility on the overall spread you have in a particular region C1. So we can look at this equation, and then there are the parameters here, beta of I are the parameters here in this particular context here. This P refers to a particular region you have here, and delta is the parameter that was introduced here to understand the impact of travel in that context. So we can do some mathematics here. We can linearize the model. We can represent this in a very nice linear system here. And then we could take this linear system here, and then we can talk about how do you determine these weights you have. That is what is the machine learning that is applied here to be able to understand what are these weights, beta and delta you have in the model. And then we learn these models by using weighted least square minimization here. And that is what is the lower right-hand side I'm showing here. Also in this process here, there is also one more parameter that we have introduced here, the parameter alpha here. It's called the forgetting factor here that is used in these models here. So we want to have a decaying weight on the past data so that as we advance in time, we want to look at what is currently happening, give it a higher weightage for the current events, current data compared to what happened a long time ago. So this is the big picture of what the modeling we have done here. Just to keep in mind here that this particular model, we explicitly model the impact of travel. And then we also have various states in the model. We also linearize the model here, and then use a particular kind of a training technique here to understand by using the weighted least square approximation or the minimization here to be able to understand the factors. There are also several hyperparameters in this training process. For example, the parameters here are, there is another parameter J I have introduced here, which you can go into in detail in our archive submission. This is a particular hyperparameter here. We also have this parameter alpha, and also another parameter here, K, which is the number of states you have. This is all hyperparameters that we vary here as part of the training process to be able to understand this model. So just giving some initial results here for the case of short-term prediction here, not including travel. So what is shown here is that there are three models I've defined here. These are the adaptive models. Whatever is our model, these are denoted by SIK, J alpha here. KJ alpha are the hyperparameters I talked about earlier. We can also fix these parameters for all the regions, or you can have variable parameters for the various regions we have. And I'm comparing the results against a particular model, a very recent model that was published out of China in the context of COVID-19. And that is what is that does single curve fitting in that context. So what I'm showing here is the improved performance you get in terms of the RMSE and MAPE metrics that we talked about earlier for the case of inside the US, and also by using the global data. That's what is shown in these two boxes in this table. So in general, you notice here that we dramatically improved the quality of these predictions by using our heterogeneous model, particularly the ensemble model here gives excellent results in this context. Moving along, we also looked at some of the travel data. We're looking at the travel data, understand what is the impact of travel in this. What I'm showing here is for the case of US and also the global travel here. And then I'm showing here by using with travel and without travel, how does our model behave in that context here. Also, I'm considering here the variable one as well as the fixed models. The variable one, just to recap, is the one in which you define individual models for various regions, various states, for example, or the various countries you have. Once again here, by using the travel data, we can get more accurate predictions compared to the previous case in which we are not using the travel data. Also, there are some small discrepancies in the table you will see here in terms of variable versus fixed or with or without travel. Some of it also depends on the hyperparameters that we use in this modeling, and that also impacts the overall quality of the results, accuracy of the results you produce in that context. So moving along, we can also use this. For example, I'm showing here to predict what happens over the next 5 days. I've just shown here some sample examples of inside the country as well as in the global context. We can get very accurate predictions by using the model. I'm just showing here some examples. And if you look at our archive paper, you can get more details of the kind of examples that we have, the kind of results we can get, accurate results we can get by using our model. There are also a number of applications of this model. For example, we can understand the present scenario by looking at what happened in the past and by looking at what happens through our predictions. It's a very interesting way we can use our model. So, for example, one of the objectives you might have is that assess the effect of a region's efforts you have to battle this particular pandemic you have. And then what is the, for example, what is the impact of contact reduction that is there and the overall spread in a particular region, for example, here. So what you could do is that because our model is based on machine learning, because the model is adaptive, it captures the changes as the data is fed into the model. So what you can do is that you can get models at two different time instants and compare the models and see how the model has evolved over those two time instants. And that will be a good indication of what has happened in a particular region or a particular country, for example, in terms of what is the impact of a particular kind of a policy that might have followed locally at that point here. So I've just given an example here. We defined the notion of a contact reduction score to capture here what is the impact of social distancing and how did the model change. So we can take these models, aggregate these models. So for example, we can look at a particular time T0 and a particular later time T1 here, compute the models at those times T0 and T1, and then look at some aggregate features of those models here. And that can be used to understand what is the impact of a particular kind of a strategy, for example, contact reduction and the overall spread in that context here. So essentially, by looking at the model itself, how the model is evolving over a period of time, we can use that as kind of a window to understand what is happening in a particular situation because of a particular kind of a social order at that point. So I'm just showing here for the contact reduction score metric that I defined for the case of the global scenario here, showing that what is the impact in the different regions here. I'm just looking at a particular window from March 21 to April 10th here. The higher CRS means it implies it's better situation at that point here. And then the highest score in this case is equal to 1. So various countries is shown here how they behaved at that point. What is the impact of that? By looking through the model itself, comparing models at those 2 points, March 21st and April 10th, we understand what is the impact over that period with respect to the contact reduction over that period. So I'm also showing here, we can use our models to understand, do some more forecasting. We can also do some more of what if scenarios we can analyze here. For example, we can develop the models over 2 different time intervals with and without the release of the particular social restrictions that may be there at that point here, and use that information to be able to compare, understand if you were to release all those restrictions we have, for example, what could be the potential impact of that. I'm just showing here what would be using the model up to that point, let's say up to say April 5th or so, the green lines that show here what is going to be the forecast if we don't release any of those restrictions at that point. And what is shown here in the red is what happens if you release at that point. So for doing so, we use the models before that particular restriction was placed, and then at that point predict, extrapolate, predict based on those models that we had, the earlier models we had at that point. The variation you see here is depending on here, how do you train the models, what kind of hyperparameters you use here that impacts the particular predictions, what if scenarios that you can predict out of that. So I'm also showing here that whatever results I showed so far assumes that we have the actual reported cases. We can also use our models to understand how do you take into picture here in the model unreported cases. We could do that. For example, we can historically look at the ground truth and some data that may be collected by using antibody studies. For example, Los Angeles Times had an article, I believe about 10 days ago, they did some local studies. So we can, based on that, we can come up with some factors here. I just defined a factor gamma here in terms of estimated total cases divided by reported cases. So we can use this information, feed that into the model, and then we can scale our results accordingly based on those constant factors. These factors may be dependent on the particular regions you have, and use that information to be able to get what could be the actual number of cases as opposed to the reported cases at any instant in time. So let me kind of summarize here what we did here in terms of the big picture. So we defined this particular model, which is an extension of the classic models that was there. This model explicitly captures some specific features that we are facing at this time in the context of COVID, including the mobility factor, and also the factor that the infected people could be in various states. We also explicitly use some information such as, 14 days, for example, 2 weeks is the quarantine period. So we created the states, we defined these models. So we introduced these two parameters, delta here and beta functions we had, which captures here the current situation with respect to the COVID pandemic. So we can also, the traditional models are not adaptive. So we have made our model more fine-grained. We have made our model to be heterogeneous to be able to capture this here. We also learn these parameters, beta and delta we have in the system. And we also have various hyperparameters that we use here as part of that, so that our whatever is our predictive model that we are coming out of it does not do overfitting in that context. So that's kind of the big picture of where the machine learning techniques have been effectively used in our model to be able to get highly accurate predictions. And some of these predictions have been given more accurate results compared to some of the state-of-the-art models that have been proposed recently in this context. So let me quickly tell you about a tool that we are developing. This is just a shot of this tool. I've shown here a particular URL here, where if you're interested, you can look at this, download this tool from there. Again, I would like you to warn you that you want to be careful about this tool. This tool gives you a lot of control here in terms of how do you train these models, what models to use, what data sets you use. This tool integrates various data sources. It also gives you some sample models to work from. You can also visualize the data. So I encourage you to visit this site, but be careful if you do use this site for any of your predictions you might make. Let's move along. So we have done this prediction. We developed this model. We are able to show that we can get some very accurate results. We can also use the model to make some predictions about what if scenarios that you might have here. We're also extending this model. Again, a lot of it depends on the data sets we can get. We can look at more fine-grained level, a county level, city level, or neighborhood level if the data is available to us here. And then we also need to understand this hyperparameters and parameters we have in the system. The training that we perform here, the quality of the results you get depends on these hyperparameters, what kind of training we do here. We are conducting more experiments here also as to be able to make sure the quality of the results, accuracy of the results are good in this context. We're also incorporating unreported cases. I gave an example of doing that. We can also extend our model to be more accurate with respect to these unreported cases as well. Now, let's see what happens beyond this prediction. Predictions is part of the initial part of our work here. We can use these models to do resource allocation. For example, we can look at optimization problems that come here in terms of what is the optimal way to distribute the available test kits, for example. What happens when you have continued lockdown? What is the optimal way to distribute in that context? We also have done a lot of work in the context of network diffusion immunization problems. So we can also look at, for example, how to limit mobility in this context so that epidemic is contained. So we can look at those kinds of problems as well. We can also generalize these models. In fact, there are some specific cases about the way this particular epidemic is spreading. Maybe we can make our models even more accurate for the future in terms of defining more general models that could be used in the future for other possible predictions. So before I conclude, I would like to acknowledge the National Science Foundation. They're funding part of this effort recently, and also the initial work that we did in the context of preparing the data sets, running some models, providing the user interface. Actually, a lot of undergraduate students at USC worked with us. They have been extremely helpful in this context for us to be able to quickly produce these results here based on the currently available data sets in this context. So let me make some concluding remarks. So we started out here by defining a very accurate model based on some earlier work that was done in the group. Based on that, we extended the model here. While we're doing this model here, we look at the historical data, use the data to be able to learn the model. We constantly update the model here. The results we get is as good as the data we have provided as input here. So we need to get accurate data in this context, use the data to be able to develop these models, continuously train the model, and they use the model itself to be able to understand what is the impact of various scenarios that is currently in a particular country or a particular region here. So the model constantly evolves in our case. It is not, we're not doing one curve fitting, we are understanding, and then we also have this factors included in this so that the model is accurate, is more responsive to the more recent data compared to historical data that may be affecting the model in some other models that is in the literature here. Also that we have several models for individual regions. A combination of those models, ensemble approach is likely to give a good result in our predictions. So let me stop here. Thank you all and be safe. And then I'm ready to take any questions if you may have any questions.
Thank you so much, Dr. Prasanna. So we do have a few questions coming in through our chat box and our Q&A. But before we get started, would you like to introduce your colleague?
So I would like to introduce my colleague, Ajitesh Srivatsava. He was one of my PhD students. He was one of the winners of the DARPA challenge in 2014-15. He did a very interesting thesis looking at network immunization problems, network information propagation problems, all in the context of data science and machine learning. He's also a senior research associate in my group at this time, and is a key author of the work that I'm presented here today.
All right, thank you, Professor. So I'll read out the question and direct to you. So first question we have here is, may I know your approach on modeling selection for this COVID-19 prediction problem? How exactly did you land up on SAR model, and why did you go for building a specific model for this problem instead? So maybe I can answer that because it's a modeling specific question. So to clarify, we did not use SAR model. We used something similar. It is a generative model that we use, which tries to define the dynamics of how things are evolving. And so what we have is what we call SIKJ, alpha model heterogeneous infection rate. And then after that, there's various choices that you have to make, and you can read that in the paper of how different choices affect the forecasts. All right, next question we have is, what health systems or governmental leaders, if any, are using your modeling to help manage the response to the COVID outbreak?
So let me answer that. I think we have provided this tool, user interface tool is there. Like I made the caution earlier, it has to be carefully used. As part of the NSF initiative, we have made some arrangements. We are discussing with various agencies, including CDC, for example. So we will make versions of this tool available, and we'll also work with them so that they understand how this modeling is done, what parameters we have chosen, the impact of training in the process. So it has to be carefully used in that context. We're also talking to various schools inside USC, which have also interest in this particular tool, particular way of modeling. So there is activities at the county level that we are working with, Los Angeles area, for example, and also at the global level working through CDC.
All right, then again, we have an implementation question. How long does your model take to converge, and on what resources? So maybe I can answer that.
Sure.
So this is a simple least square problem. So the convergence is always guaranteed, and it takes a few seconds. And I did the implementation on online MATLAB version, thanks to USC for MATLAB license. So yeah, it takes a few seconds to converge for even if I'm doing for all the countries at the same time.
Fantastic. Do we have any other questions? You can either enter them in the chat box, the Q&A box, or even raise your hand as a participant. Great. Viktor and Ajitesh, I think your presentation was so thorough that it answered all the possible questions that everybody could have had. Fantastic. Okay, is there anything else you'd like to add before we conclude?
All right, thank you very much. It has been a very nice work that we're doing in the group. I'm really very pleased to have Ajitesh as part of the team, and also that we're looking at a lot of interesting problems that come here in this context. National Science Foundation is very interested in this problem space. We're also working with our colleagues at USC, computer science, electrical engineering, as well as ISI. And we're looking at some very interesting problems here in the context of what happens if you release those orders at this point. Can you make some predictions in that context? What is the optimal way to allocate resources? These are very important problems. We are in tough times at this time. We're also very excited to see that our techniques from Data Science Lab, in general, machine learning techniques are very valuable at this point. Thank you all.